Welcome back to the classroom. My name is Mr. Wong, and today we're going to look into conservation of momentum again, same as last lesson, but this time we're going to be focusing on the different types of collisions that will occur. So just a recap from before, we talked about different ways that momentum is conserved in a collision. There are three types of collisions that can occur. The very first one is elastic collision. So that's in the scenario where two objects collide and they remain separate after collision. Now, in reality, a lot of collisions can appear to be elastic, but there is some kind of inelasticness that does happen, which we go into this one. So inelastic, or so to speak, complete inelastic collision is when two objects collide and they combine together. Now, what you can see in this animation here is a partial inelastic collision. So there is deformation, but you can see the two objects do separate over time. So that's what I was saying there. Often, some collisions that we might see where they collide and separate might look like elastic collision, but it's actually inelastic collision. And in actual reality, we don't really see elastic collision in real life at all, or close to zero. The main reason being is when anything collides, there is some kind of transformation of energy in the form of heat, in the form of sound. So that's two types of collisions there. The last one we have is explosive collision, and that's when an object breaks into multiple components. So that could be, a bomb detonating and then exploding. So that's what we mean by that. There were three formulas that we can use to explain the different types of collision. Each one follows the law of conservation of momentum. So the idea is very simple. What momentum we have at the start of the collision has to be the same at the end of the collision. So what I can say is, let's say the original momentum was 0 at the start of the collision, okay? Because, one car was moving this way, the other car was moving this way. After collision, they bump off in two different directions. That total momentum of the two sides should still also add up to 0, because the initial momentum has to equal the total final momentum, and that number is constant, meaning by it doesn't change, which also means momentum is conserved. So let's have a look at some questions that can use these equations and go from there. Okay, so we're going to start with an inelastic collision, though obviously you don't get told that in an exam. You need to be able to understand if it's elastic or inelastic. So let's have a look. We have a 30-gram bullet, okay? So that can be mass 1 for me, traveling at 250 meters per second. So that's my initial velocity. Fired at a block of 4 kg and gets embedded in it. So if it gets embedded, that means they kind of become one single object. So what I'm dealing with here is an inelastic collision, or I can assume it is. The block swings and rises through a vertical height of h before coming to rest at 0. So has a 0 final velocity, so to speak, at that point. Okay. So the first question says calculate the initial kinetic energy of the bullet. So what we have here is our kinetic energy is equal to half. Kinetic energy is m, mass, times velocity squared. Now I'm just going to write the same symbols as I labeled here. You can write half mv squared here. It doesn't really matter too much. So half times my mass, which is 30 grams. You do need to convert that in the correct SI units, in this case kilograms, and then 250 squared. So there we go. So the answer I get is 937.5 joules, because that's my SI units for energy. And that completes the question there. Question B, it says determine the speed of the block immediately after the collision. So if we're talking about some kind of collision analysis, we would look into the conservation of momentum laws in collision. In this case, we said it's an inelastic collision. So we are going to use the inelastic formula to help us work that out. I do need to emphasize though, there are multiple ways to determine if a collision is elastic or inelastic. We will go through that later on when we talk about kinetic energy. So if we have an inelastic collision, then the mass of 1 and the mass of 2 will add together because they get embedded into the same object. Hopefully that makes sense. So the mass we have 0.03 with initial velocity of 250 plus 0 because our wooden block was originally not moving, okay, equals to our new mass 4.03 multiplied by v. That's what we want to find. So in this case, v is equal to 0.03 multiplied by 250 over 4.03, and that gives us an overall momentum of 1.87 meters per second. And that's how you do question C. So the next one we need to do, just draw a line down below. Hopefully I have enough space here. Question C is asking for the kinetic energy of the bullet and the block after collision. So same formula, kinetic energy equals to half. Now the mass we're going to use here is the embedded mass. So the mass where the bullet and the wooden block combine together. So it's 1 plus 2 plus v squared. V squared, obviously the number we just found over here. So half 4.03 multiplied by our velocity 1.87 square, and we get a energy of 7.05 joules. Question D, it says find the value of h. Now remember the scenario we talked about before. When they collide, the bullet is going to force the pendulum upwards, sort of like in a circular arc, and it goes like this. So it's going to reach some certain height from there. Now if you recall what we talked about with motion of pendulums, that originally the object down here, if we assume that's the starting height, okay, so let's say this is our 0 point here, there is no potential energy. The motion to cause this pendulum to move is obviously kinetic energy, forcing it to move upwards, okay? So that means what we have here is a transformation. We're getting a transformation of kinetic energy into gravitational potential energy to take it to the very peak height. Or at least we're assuming that's what the question's asking us here. So we're expecting a 100% transformation. How do we know it's a 100% transformation? Because in this question here, it says the object comes to rest. If it comes to rest, according to our kinetic energy formula, there is zero velocity, meaning by there's zero kinetic energy, which should imply that it's reached its maximum potential energy. So when that happens, we can safely assume that it's been a 100% transformation there. And obviously, as we said before, the reason why we know that's the case is because law of conservation of energy. So D, we know that kinetic energy in this case will equal to the gravitational potential. Now the gravitational potential is mgh. In this case here, m is 4.03. The g value is acceleration due to gravity. H is what we want to find. The value for energy is 7.05. So if I rearrange my equation around, so I'll just show that working out there. From this point here, you can sort of just skip towards the answer, I guess, but good to show you in case you're not sure, that rearrangement. So we get a value of 0.18 meters. And that's how you do this question here. So, quite a lot of steps, but it is utilizing our understanding of conservation of energy and also conservation of momentum. In this context, for inelastic collisions. Okay, the second part of this lesson is looking at the conservation of kinetic energy in a collision. Now, the main point of looking at conservation of kinetic energy is to compare elastic and inelastic collisions. So as we can see here. Now, you know Newton's cradle, it looks relatively elastic, but as we said earlier in the piece, that you don't really ever get 100% elastic collision. Generally, it looks something more like this. You can see a separation between the two cars as they collide. So, it sounds like the definition of elastic, but you can see there's deformation in the structures of the car. And so that would imply there was some inelastic collision that also happens. So when we use the formulas for conservation of momentum, we can make assumptions if it's elastic or inelastic. But in order to prove that it has a complete elastic or inelastic collision occurring, we have to compare the conservation of kinetic energy. So I want you to kind of understand this. In order for elastic collisions to have actually occurred or prove that an elastic collision has occurred, the kinetic energy is conserved. Okay? It's not a scientific law, but it is an observation. So I'll just write that down. So conservation of kinetic energy is not a law, but it is a way to prove whether or not an elastic collision has occurred. So, but can be used to prove if elastic collision has occurred. So just keep that part in mind, okay? If we kind of look at the mathematics of it, let's say, two objects have collided with each other and we want to compare the kinetic energies before and after. So we have the formulas here, the original or the final kinetic energy of object A subtracted by its kinetic energy initial. Same thing for object B. We round it off. We can see this is the formula we have down here. If we then want to rearrange the formula around, okay, we want all the initials, initial kinetic energy on one side and all the final velocities on the other side. So say, for example, this final here, this final here, we're going to move it over here, and the initial that we have here, we're going to move it over to this side over here. We can rearrange the equation to look something like this, and we get something like this. Okay, so this form that we have here is the conservation of kinetic energy. Now, this is only true if we have an elastic collision. Now, by all means, you can use the conservation of momentum laws to do calculations about the object's velocity, because momentum is always conserved. However, you cannot use that formula to prove or solve that an elastic collision has occurred. You need to demonstrate that kinetic energy has been conserved. Okay, so what does an elastic collision actually mean? Well, it actually means that there is a 100% transfer of kinetic energy, meaning by when two objects collide, okay, so when they kind of come together here, the kinetic energy of, collision 1 is transferred to collision 2 and vice versa. in that process, no energy has been transformed. So we don't get sound energy on that collision, so I can't hear the collision occurring. There shouldn't be any heat formation. There shouldn't be any elastic potential, so there shouldn't be any deformation. That's what we mean by elastic collision. Okay, and also we talk about inelastic collision. So we've talked about what the formula of inelastic collision looks like, but in order for an inelastic collision, or to prove an inelastic collision has occurred, we need to demonstrate that the change in kinetic energy is not equal to each other. Or, so to speak, the energy or kinetic energy is not conserved. Now, I do want to stress the fact that conservation of kinetic energy is not a scientific law. It is not something that we always observe. Remember, a scientific law is something that you continuously can observe in no matter what system you're looking in. So it's not a scientific law, but conservation of kinetic energy is used to demonstrate if a collision is elastic or inelastic. Okay. Now, the reason why kinetic energy is not conserved in an inelastic collision is because, as we highlighted before, it could be because of heat loss. It could be the transformation into sound energy, or even some other forms of potential. In this case, usually elastic potential. Okay, so let's do a quick conclusion here. If we have an elastic collision, momentum and kinetic energy are both conserved. So momentum before and after are equal. Kinetic energy before and after are equal. Collisions which kinetic energy is not conserved, but momentum is conserved, is what we call elastic. So momentum conserved, but this is not conserved here. So a little quick summary of that is just to say that the change in momentum is 0 in both cases for elastic and inelastic collisions. However, the change in kinetic energy when two objects collide is not the same. So for elastic, the change in kinetic energy is equal to 0, or there will be no change. The change in elastic collision would not be equal to 0. Okay, so a simple conclusion we can make is for both collision types, elastic or inelastic, the change in momentum is equal to 0, meaning by it's conserved, meaning by one is equal to another. For elastic collision, the change in kinetic energy will also be equal to 0. It is a constant, but not for inelastic collision. That will be different and will not equal to 0. Okay, so let's have a look at an example of where we might assess if a elastic or inelastic collision has occurred. We have a skater, 60 kg skater, traveling at 4 meters per second. Let's say they're going that way. We have a 40 kg skater that is going in the opposite direction. Or well, technically in this image, they're both moving in the opposite directions there to what I wrote. So let's say 60 is going to the left. That's what I have in the image down here. And the 40 kg skater is going to the right. So that's what we have. They collide and bounce off each other in the opposite direction. After the collision, the larger skater moves at a speed of 1. Let's call that V1. So we'll call you U1, and we'll call the second skater U2. But the smaller skater has a speed of 1.5 meters per second. So we'll call that V2. Okay. Is this an elastic or inelastic collision? Prove with relevant calculations. Now, firstly, we need to make it very clear we can't use the conservation of momentum formulas to derive whether or not it's elastic or inelastic. That's a common mistake. We need to demonstrate by comparing the kinetic energy before and after the collision. Okay, so that's what we need to do. So let's go through it in the following slide. If we have an elastic collision, that means that my kinetic energy initial must equal to my kinetic energy final. Okay, so if I work out the formula for kinetic energy, that is half mv squared. Now, in the context of what we're doing here, okay, so the initial would be mu1 plus half mu2 square. Okay, so that's what we have here. So this is the following calculation I have. Now, I already said that one is moving in the opposite direction to each other. So that's why one is a negative value for velocity and one is a positive value. That's to indicate that they're moving in the opposing direction. But you do need to remember that energy is a scalar quantity. So if it's a scalar quantity, regardless, we should have a positive value at the end because energy does not have a direction, which, helps because, we got to square the velocities anyways. So that's 1,200 joules. If I compare what they have as their final kinetic energy after that collision, okay, this is what we get. The 60 kg skater goes at 1 meter per second in the opposite direction, and the 40 kg skater goes in the direction of 1.5 meters per second in the other direction. And they travel, or that total kinetic energy used up was 75 joules. Now, obviously, if we compare the two here and here, they're not equal to each other. The initial kinetic energy is much larger than our final kinetic energy. So therefore, this is an inelastic collision. Okay, so that's what we have there. Let's try another question. So here we have a collision here. Let's go through the reading. We have a steel ball, so that's one of the masses we need to take into account. We use ms to mention steel ball. It travels at a velocity of 2.2. We'll call that us, or you could call it u1, I guess. It doesn't really matter. It's just the annotation as I have in the other slide that will help. So we have, it collides with a rubber ball. Okay, so there's that, mr 0.5, and it's moving south at that particular velocity. We're going to call that ur. Immediately after, the steel ball is going in this particular direction north, so that's its final, and the rubber ball is going also north, upwards there. Okay, so there's that. What we can see is in this collision, one is still going in the same direction, and the other one is moving in the opposing direction. So it could be potentially elastic, it could be also partially inelastic. Let's have a look. Let's just start by saying the north direction is my positive direction. Okay, so I just do my substitution here. And I find that the total kinetic energy is 20.4 joules. That's for the initial system. Now, after the collision has occurred, I do my substitution again. And I find that the total kinetic energy is also 20.4 joules. So what that means is, because my initial kinetic energy is equal to the final kinetic energy I have I'll say that again, in my system, that means I have an elastic collision. Excellent. So that's how you do those kind of problems. If you need to solve for if something is elastic or inelastic, you will need to use the kinetic energy formulas. If you want to try and work out the velocity before or after collision, then you would be using the conservation of momentum formulas. So that's the difference that you'll need to take into account. And that concludes our lesson for today. So we've gone through the different types of collisions, or collusions, I'll change that. So we've gone through the different types of collisions. We've talked about how in order to have an inelastic collision, momentum is conserved but not kinetic energy. An elastic collision, is where both kinetic energy and momentum is conserved. Now, all these scenarios that we've talked about up till now have been for one-dimensional collisions. I might do a video later on where we demonstrate collisions in 2 dimensions and see how we can solve for those type of problems. But until then, thanks for listening up till now, and I will see you next time. Take care.